Okay, so I know on the calendar there is an exam review that's done in class on Wednesday, so this upcoming Wednesday before the exam. We can pull the class. Do we want to do a session out this week, like so tomorrow basically, to review, or do you just want to go off of Wednesday?
Tomorrow.
Because Sundays, I Sabbath on Sundays, so I will not be available on Sunday. But I could do Saturday in the evening sometime after 4 o'clock. Okay, raise your hand if sometime after 4 o'clock you can do a meeting tomorrow. Okay, so let's think about this. Presumably you should all eat and take care of your bodies, because it's the temple of the Lord. So eat some dinner at 5 o'clock, and then maybe we'll... Okay, actually, this could be fun. If you want, optional, this is not part of the review. I will go to Saga tomorrow at 5 o'clock for dinner, and if you want to come join and have a class Saga before we go over to the GC, you know I love to eat food with you guys. So let's do that. Then let's plan on actually starting the review at 6 o'clock in this classroom. Okay? Does that sound good? I will record it because some people have jobs, some people have family and other things to attend to. But does the majority can make tomorrow 6 o'clock in here? I need a thumbs up. I need to see that. Okay? All right. Today is 2.4 partition matrices. Now, this is kind of it's just a fun relationship between what we've been doing and then actually more applied related computer science stuff. But, so if you're computer science, you might find this cool. You might be able to use this in computer engineering projects if you enjoy building your own like Raspberry Pis and things like that. And for engineers, I know that a lot of you guys are engineers, lots of different types of electrical circuits, lots of electronics, lots of those kinds of things that when you're working through calculations, especially Kirchhoff law calculations that get really bad, imagine scaling that up to the size of like a Boeing 747 now, okay? So that's obviously millions upon millions upon millions of systems of equations that are all happening. Millions of circuits, probably. So you don't want a matrix that has a million rows and a million columns. That's just terrible. And so partitioning is going to help engineers take different parts of these control systems, parts of these circuits, and then localize them. And then their relative relationship to each other overall on the motherboard can be then the overall matrix. Okay, so just the basic at a glance concept of that's a big matrix. I don't want to deal with that big matrix, and I break it down. That's partitioning matrices. Okay.
It's just data collection.
So let's recall that if I have some Aij matrix, that what we've been doing, we've been doing this since the beginning of the class, we can think of it as a list of column vectors. You've seen that probably 10,000 times now, okay? This is definitionally a type of partition of the matrix A. Because what I've done is I've decided to view this matrix A as a bunch of, essentially, submatrices. And we happen to call them column vectors because column vectors have very specific dimensions and properties, and they're very useful to work with. But for all intents and purposes, you've already interacted with partitions, okay? So don't think that this is entirely new. It's just going to more generalize what we've already been doing. So we could view, I already said that. So let's do the example. So if I have some A, 3 minus 5 minus 8, 0, 2, minus 6, minus 1, 4, 3, 5, 0, 1, 9, minus 3, 7, minus 2, 1, minus 4. What I can do Now, obviously, I have to scale it down in size for just practicality in a lecture, but this could be like a 27 by 45 matrix, okay? That's a pretty big matrix. This can be, and also this can be written as, I can collapse this entire matrix into just a 2 by 3 matrix. So it can be written as the 2 by 3 matrix actually I'll put the definition here first so that we can see it. Partitioned matrix or block, because they're like building blocks matrix. So partitioned or block matrix. And then the individual blocks themselves could be thought of as a sub-matrix. Now, one way I could partition this, and the way I'm going to do it isn't the only possible way. It's just one of many different ways you could do it. So I can think of partitioning off the top 2 rows like that, and then have these 3 columns like this, and then 2 more columns like that. And if you really think about it, then I have reduced this matrix into a 2 by 3, where each one of those entries then is a submatrix in itself. Okay, so it's just a perspective switch. I'm not changing anything, I'm not doing any computation, I'm not changing any numbers. All I'm going to do is I could say, let's assign to each one of these blocks a submatrix. So I can call A1. So the first subscript, the subscripts are going to follow the ways that we've been doing the addresses. So in the first row and then the first column, A11, that submatrix is 3 minus 5, 0, 2, minus 1, 4, and then that's it. So that's a submatrix. And then I could have A1, 2, which signifies that I want row 1, column 2. That's row 1, column 2. So somebody tell me what's going to be this A12 submatrix?
5, 0, 9, negative 3.
5, 0, 9 minus 3. And then lastly, on the top row, so first row again, A1, 3, so third column is what?
2, 1.
Yeah, minus 2, 1. Okay, so now let's look at what the next row is.
2.
So A2 for a second row, 1 for the first column is going to be what?
Negative 8, 6.
Yeah, just written across. So minus 8, minus 6, 3. A 1 by 3 matrix. In the second row, second column is what? 1 second. And then our cute little A2, 3 is what?
Negative 3.
Minus 4. Okay, so if I think about this, I can now take a 3 by 6 matrix, make a partition. This is arbitrary. You could have split this up any way you wanted. And now express it simply as a 2 by 3. So A11, A21, A12, A22, and A13, A23.
Scott,
Yes.
is there a subscript that you put on edge that signifies it being the partition matrix? Is there one that's why?
Are you asking about the original matrix or the actual blocks themselves?
I'm asking about the capital A right there. Is
This
there
one?
like a A of P or A of PR that when you know that when it states A of PR, we know that it's the partition matrix?
Oh, that's a good question. The answer is no. And the reason why it's no is because a key thing for this concept is that partitioning it ultimately doesn't change it. It's just a shift in perspective. And so I'm not going to modify the notation to A, because A is still referring to precisely this matrix. And just because I've chosen to write it using these blocks doesn't mean that when you expand each one of those and see the numbers, it's going to be a carbon copy. So that's why we don't subscript or denote indicate whether it's partitioned or not, because the choice to partition is entirely optional and a perspective thing. Yes?
To make sure, if we deleted the line that's separating A1, 2 and A1, 3.
So deleting this line?
Yeah,
okay.
Would it turn into a 2 by 2 matrix, meaning that it would just be like a 2 by 3, 2 by 3.
Yeah, so think about this. If I get rid of that partition marker, then now I've just made my blocks like this. This is a block in A11, and now this is my other block in A12. And then these become the bottom two blocks. So that's why the idea is, this is just an example. I have to pick numbers, I have to pick an arbitrary partition so that you can kind of see. But yeah, you could have done that however you wanted. So keep this up so I don't get confused with my notes. For this is kind of a way I like to think about it. This is your mom's cooking blog. And when you go on, she has her list of recipes that you can go through, right? But is she going to put as the title on the link the entire recipe instructions and have like a 7,000 character title? No. She's just going to say what you're cooking, right? And so that's kind of like what these blocks are. And so you can imagine, and you click and open a link and be like, I want that recipe. Bingo. Stores that information for you. So it's like a way, this is a really convenient way to condense massive amounts of information in really, really small matrices. Yeah? Okay? I don't know exactly how computer science works, as evidenced by the fact that I'm like currently failing Java intro, but I would presume it would be really, really fantastic of an algorithm if you had to store a bunch of different data but didn't want to have to keep it all at the same time. So if you partition your data and then just simply call upon the partition you're interested in one at a time, that might make it faster. Again, I don't know if that's actually how it works, but I'm just trying to help you brainstorm for the application side of this, okay?
Could we partition our partition matrix?
Well, let's answer the question by doing it, yeah? Let's make a partition like that.
Let's be a 2 by 2 matrix now.
Okay, so now, do we want to cut it up again or leave it? Cut it up again?
Yeah, let's cut it one more time.
Like that? Why cut it? If you cut it again, you just have It's like, I want to, that's like disassembling, you rage quit on a Rubik's Cube, so you take the pieces apart just to put it back together again.
That's easier.
Okay,
Yeah,
so
together solve.
if I want to think of this, okay, so now I need to come up with a different notation for my blocks. So maybe I use B. So then this, I want in the first row and first column, that is going to be A11. And then if I want, then how do I call this one? So in the second row and the first, that is the matrix, the block of a block, A21. And then B, so now if I want this guy, so that's in the first row and then second column, then this is actually a little bit bigger of a submatrix, right? Because then I need to fit A12 next to A13. And then for the second row and the second column, I need to fit A22 and A23 next to each other. So I'm just now viewing these submatrices as numerical entries themselves. It's just these objects. And so now I could think of this matrix as a 2 by 2 matrix. B11, B21, B12, and B22. So you can say you need to store data in a matrix that has different dimensions than what you're originally given. Just partition it and custom fit your dimensions that you want. Yeah? Because what did we start with over here? Matrix dimensions-wise, A. How many rows?
3.
And how many columns?
6.
Okay, so say we didn't want to store our data in 3 by 6, and we do this A partition. Now, what kind of matrix is it with this partition?
2 by 3.
Yeah, so now we're storing it in a 2 by 3. And then if we wanted to even partition further, we're storing our data in a 2 by 2. This brings me to a key point. Do not think that there is some sort of pattern to collapsing a partition to like multiples. Okay, so you might be tempted to think, well, 3 by 6 went to a 2 by 3. Maybe there's some sort of relationship. Or you could take maybe a 3 by 6 down to a 1 by 2. That doesn't mean that's the only way you can do it, okay? Because obviously, 2 is not divisible. You can't divide 2 and 3 together. They're not the same. A square is not proportionally the same as a rectangle right here.
This might be wrong, but I remember like last chapter we were saying that because we couldn't make a pivot point on all of them, we technically always have a free variable. So therefore, can we now make like thick matrices always have a pivot point in every row in this way, or is that wrong to think about?
Well, definitionally, pivots have to do with the actual individual entries themselves. So notice that once you've partitioned the matrix, these are no longer the actual individual entries. And so definitionally then, we're not thinking of that as a pivot. We're thinking of that as a block.
But isn't there a way to, okay, again, probably wrong, but isn't there a way to make like solve every matrix to make it into a number, then by making that to a number, it will be a numerical value in it, or is that wrong?
No, the inherent properties of A, if you never partitioned it, will be the properties of A after you partition it.
Okay.
Because so what we're doing with partitions is we're not modifying the actual matrix.
We're just cutting it up.
The matrix is exactly the same. It will have the same properties. Partitioning it will not change A's properties. So if you started with A being invertible and you partitioned it, you didn't accidentally break it and now it's not invertible anymore. Because the matrix is still just A. And counterwise, right, if A has infinitely many solutions and then you decide to cut it up and store the data in a different partition, well, that's okay. It still ultimately has infinitely many solutions. So you're not altering its properties, you're not altering its algebraic properties. The only thing you're altering is just convenience and computation for later down the road. Does that make sense? Okay. Anything else on this? Okay. Well, let's do some algebra. Okay, let's look at addition first because that's the easy one. Say I had a matrix A, and I was able to partition it as such. It's like A11, A, it's like 2 1s. A12, A22, A13, A23, and A14, A24. And say I took another matrix B that had the same dimensions, and then further made sure that my partition preserved the dimensions respectively for each one of these. B11, B21, B12, B22, B13, B33, B14, B44. What am I doing?
Yeah.
B23, B24. So, provided that you've done the partition in a way that the dimensions of each of these blocks are the same, in other words, that addition is defined, then you could choose to add A plus B as you typically do, where just original matrix and original matrix, or that will be equivalent to doing adding up all these individually. So A11, B11. That upper block will be the same, equivalent. Again, this is when you really look at an individual computation, it becomes kind of like, well, yes, obviously. A12 plus B12, B22, well, I should have done A first. A22 plus B22, A13 plus B13, A23 plus B23, A14 plus B14, and A24 plus B24. Okay. You might think, wow, that's really inefficient when you could just do basic addition from the original things. I agree, minus the fact that sometimes, again, in real life you have a matrix with, several hundred, several thousand, million, these orders of magnitude of entries that are just too massive. And sometimes when you use a computer, like when you open your laptop, do you instantly open every single application and then just fry your RAM? No, of course you don't do that, okay? What you do is you only open the applications that you need one at a time. So say you wanted to perform a computation that related this massive hunk of data and this massive hunk of data, but the only thing that's actually being affected that you're interested in is just one specific block of that. You just partition that block out, find the respective partition over here, do the computation, ignore everything else, and it'll still have all the same properties as if you had slammed through the entire computation, okay? So this is issues of efficiency when you can, not prescription of this is the only way you should do it from now on. Does that make sense? So contextualize your tools. You don't use hammers for everything, you don't use saws for everything, you don't use partitions for everything, okay? But when it's useful, use it. Especially if you're doing group projects or senior projects or all those fun things.
To me, it makes me think of when you have a whole bunch of variables that you've collected a lot of data on a whole lot of different variables, but maybe we're not interested in that part right then. So we'll just use the columns and the rows that are of interest to us.
Okay, so let's get to the fun part, which is multiplication.
Can I?
Yes.
So is there a way for, like, going back to like the senior project idea, so if you had like a senior project, would it be possible to like say that like A is the original, then you have B, that's the way that if you had a constants on those, therefore by having a constants on those, that means those are the ones that are respective to that constant, and you can have C with the same matrix or the same rows and columns with different constants, that when those constants are interactive at that point, you know what I mean? So you like sort your constants or sort your data through the ABC matrix idea?
Scalar multiplication doesn't change on a matrix. So if I wanted to scale A by some scalar C, then every single entry within A is going to be scaled by C. So that doesn't really have to do with the partition per se. If you're asking if I scaled C here, could I think of scaling now a block by that scalar C? Sure, you could. I wouldn't make that a senior project though, because the proof of that senior project would be citing an algebraic property.
No, I meant like if you like had like a senior project, like you had a bunch of data, is that possible?
Mm-hmm.
If you're like doing experimental, and
sure.
You're like, oh, I need blah blah blah, that needs to go blah blah blah. That means I need to times only this row by blah blah blah. But if it affects these rows, it can't. So we're gonna put in a partition that it only affects that part of the row.
You could do that if you wanted to.
Yeah, I was asking.
Yes.
If that would be.
The nice thing with math at this level is once you're given the laws. There's a reason, by the way, that I write all those out. Because it might seem like, duh, A plus B is B plus A. Duh, the distributive property. Duh. No, it's not so duh. When you want to do your own math on your own, prove your own properties, explore your own things, you gotta know what the rules of the road are. It'd be like if you learned how to drive in America, think you know now how to drive in England, and then you go head-on collision to every single car on the road, okay? So it's like, what we study in algebra, you're getting algebraic properties. You're learning the street rules. So that when you do your own math projects, you're doing your own computations, your own explorations, you actually have a framework by which you know you are obeying the laws of that mathematics. So that what your results are not only valid, but actually meaningful. Does that make sense? Okay. And that extends way past this class, too, no matter what you take in mathematics and these STEM courses. Okay. Because what we're seeing right now in STEM is people got so dependent on digital aids that they let a computer or an AI think for them in terms of what they're allowed to do. So suddenly now, if you don't understand the rules, you can be feeding into an AI a question that is definitionally nonsense. And so what's the AI going to do? It's going to do a search up on all of your terms that you threw together, make a soup, and since it's an AI, it has to answer you. So it's going to then have to invent some sort of a way to reconcile the fact that your question is, by property, false. So then now you've tricked yourself into thinking that you've come up with something and answered your question that by definition shouldn't have an answer. And then you go on and write that paper, you post something on a blog article on the internet to feed the cesspool of the AI engine, which is now going to read that, and then start feeding your wrong answer to all the other people studying that topic. Okay? So I don't hate artificial intelligence, but it's ruining a lot of this stuff. Yes. I had
It sounds like
several students 2 years ago. They were doing their DiffyQ project delayed. They procrastinated, of course, and they had fed into ChatGPT, spit out the solution of, and what they put in was not even an equation. It wasn't an equation that was like even definitionally possible. And so then the computer obviously had a stroke, and it fed them out this answer, and they were like, hey, can you verify this solution? And I look at it and I'm like, this equation shouldn't have a solution because it's definitionally wrong. So I don't know how you got here. And then they had to fess up that it was AI. Okay?
Was it ours?
No, it wasn't yours. Although that's a crazy way to fess up that you use AI on a project. Okay. Alright. Let's do multiplication because this actually is a really good algorithm for doing matrix multiplication later anyway. Let's do it on, well actually, let me think ahead. I'm actually going to erase this so that I have space to do both. Okay. This is like the only important part of the section really. So, I'm going to make a 210 minus 3, 5, 4, or sorry, negative 4 minus 3, 5, negative 4, 1 minus 2 minus 2, 0, 3, 7, and then minus 4 minus 1 minus 1. And the way that we're going to do the partition for the sake of this exercise is we'll partition off this row, and then we'll partition off these 3 columns on one side to form a block, and now we have a 2 by 2, okay? So I can think of this as a 2 by 2 of A11, A21, A12, and A22. Okay, so that's the first matrix that we're going to have. The second one, B, is going to be 6 minus 2 minus 3 minus 1, 5, 4, 1, 7, 3, 2. And you might be like, why is this one so tall? Well, because in order to do the multiplication and have it be defined, this is a 3 by 5, which means that the number of rows that the one we multiply against needs that many rows. The number of rows here has to match the number of columns here. So if I have it longer here, well, we're going to have a taller matrix over here. Okay? Now the way I partition this subtly matters, right? Because think about it. If I just choose to make my partition and block off this 1 by 2 up here, and then I'm stuck with this 4 by 2 down here, those blocks aren't going to make any sense for these. So when I think about it, A11 is a 2 by 3, which means that the corresponding B11 block needs to have at least how many rows? We need at least 3 rows. Okay? So there is some element of multiplication where you can't just pick and choose whatever you want. There are some hard and fast things. So I do need to accommodate and make sure that that top block has the 3 rows to fit and define the multiplication with 3 columns here. And that it checks out because then down here, the bottom block is a 1 by 3. Okay, fantastic. I have that 3 rows for that. Over here, a 2 by 2 and a 1 by 2. In other words, I need 2 rows, and those remaining 2 rows can then multiply against those. Okay, so just that's like the one caveat with this is it's not completely a free for all with multiplication. We have to unfortunately obey the laws of algebra. Okay, so we can think of this as B1 on the top and B2 in the second row. Yeah, because it's only one column. Okay, does that make sense why you can't just pick and choose wherever you want?
Yes.
Okay, so let's actually then go through. I'm on the wrong page. That makes a lot more sense. Okay, so let's take a look at what this product is going to now look like. So if I had done beforehand, compare the product. Imagine I took this matrix as it is in its 3 by 5 form, and this matrix in its 5 by 2 form, and then set those next to each other. Now, because, I mean, that's actually not too bad because we're talking on a smaller scale, but, you know, throw a few more zeros on the magnitude here, and suddenly that's kind of like a massive multiplication. And we can boil it down to this perspective instead. Because now my AB problem is really a 2 by 2 times a 2 by 1. Okay? So I got A11, A21, A12, A22. That's times now B1, B2. So perspectively, we've switched the problem over to a 2 by 2 times a 2 by 1. And now I can think of this, right? So this is the B1 is going to come down and be multiplied against this column, and the B2 is going to be multiplied by this column in these dot products. So we're going to have A11 B1 plus A12 B2. So A11 B1 plus A12 B2. And then on the bottom, A21 B1 plus A22 B2. So then the bottom dot product. A21 B1, A22 B2. So we can think of this multiplication as individually, oh, I didn't put a subscript on that. There we go. Computing each of these smaller products, and then those are going to now give us the multiplication, okay? So A11 B1 is, what is A11?
2, 1, -3, 5, 1, -2.
And B1 is?
6,
Right, it's this piece, the 6 minus 2 minus 3,
4,
1, 7.
1, 7.
Okay? So this is a 2 by 3 times a 3 by 2.
Yeah.
So what's the output size? 2 by 2. Okay? So I do this dot product. 2 times 6 is 12, and then the 3 minus 3 times minus 2 is plus 6, and then minus 3. So we get 15. And then I'm going to do the second row, but still in the first column. So second row, first column. 1 times 6 is 6. 5 times minus 2 is -10. And then the minus 2 and the minus 3, that's 6. So overall, that's 2. Now, I want this entry. What row is this one going to be in? The first row, and which column? So, first row, second column. 2 times 4 is 8. Minus 3 times 1 is minus 3. 1 times 7 is 7. So 12. Okay, what's the row
2.
and the column?
2.
Row 2, column 2. 1 times 4 is 4, 5 times 1 is 5, and minus 2 times 7. When I was doing my lecture notes, I actually genuinely just sat in my desk and could not figure out what 9 minus 14 was for the life of me. And I actually just forgot now. Okay, minus 5. Okay. Oh, man. That's A1, 1B1. Okay, so now we need A1, 2B2, or, yeah, A1, 2B2. What's A1, 2?
A1, 2. 0, 3, -4,
What's B2?
-1, 5, 3, 2.
Mm-hmm. Very nice. It's a 2 by 2, so obviously we'll have an output of 2 by 2. Same thing, okay? So I don't want to waste your time on just these products. We walked through that one carefully because I wanted to review that algorithm, but now I'll just put in these numbers. So minus 20, minus 8, minus 8 and 7. And then now we have information for this top thing, right? Let's get the rest of it. So let's get A21B1. A21B1. What is A21?
0, -4, -2.
Minus 4, minus 2. And then what's B1?
6, -2.
Yeah, the tall one.
3, 4, blah, 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 blah.
Dimensions?
1 by 3.
Dimensions.
3 by 2.
So output is?
3 by 2. 1 by 2?
1 by 2, yeah. Okay, and then that'll be 14, -18. A22 times B2. What is A22?
7,
What's B2?
3, 1, 3, 1, 5, 3, 2.
Dimensions.
2 by 2.
What's the output?
1 by 2.
Okay? And then that's just going to be minus 12, -2. Okay. So
That's a 9.
That's not.
I'll rewrite it. Yes, minus 12, 19. Okay, so now I can think of my A11B1, A11B1 plus A12B2 as being that 2 by 2 up there, the 15 to 12 minus 5, plus the A12B2, which is this minus 20, minus 8, minus 8, 7, which is actually kind of nice. It's just minus 5, minus 6, 12 minus 8 is 4, and then 2. And then we can do the same thing for the bottom. A21, B1, plus A22, B2. Here is A21, B1. 14 minus 18. And then A22, B2, minus 12, 19. So 2, 1. And the reason I wrote these kind of like this is because guess how they are appended in their column here, right? So then AB is that first, so that's this submatrix, minus 5, minus 6, 4, 2, and 2, 1. Now you might be thinking to yourself, well, that was stupid, because I could have done just A times B about 7 times faster than this entire rigmarole. You would be correct. But this example is important to show the mechanics for the theorem that I'm going to show. Okay, the last theorem that's part of this section doesn't really make a whole ton of sense unless you've gotten to interact with how the computations break down, why the rows and the columns go together, why you're allowed to say why it works instead of just assuming it's true, okay? So, contextualize this example in your notes as this. Don't actually solve problems like this, okay? Don't do it. But it gives you a concrete way to interact with the inner workings of the algorithm, why it actually works, and that the output can be verified. Because now we'll get to the actual important part, which is the theorem. Right on time. Let's go. Right on time. I also realized when I was planning on what I was gonna do for Valentine's Day class, and then I looked at the schedule and I was like, oh, I'm giving you guys an exam for Valentine's Day.
That's a David Matt.
You should put a rose on top of
We
it.
love Matt.
You know,
You should put a rose on top of it.
Algebra is my death talent.
You can give us +5 extra credits. That's pretty much like flower.
okay, column, row, expansion of a product AB. Okay, so if A is M by N and B, it's gonna take me a few weeks to get used to the font change. B is N by P. Why do I start it with N?
The row.
Because it has to have the same number of rows as A has columns.
Exactly. Otherwise, I could stop the theorem here, because guess what? You're not multiplying them together. So we need to make sure that I have definitionally defined multiplication. Then I can think of my product, AB, not as the relatively unhelpful arbitrary partitioning. There's a very helpful partitioning, actually. It's the row, it's taking the columns of the first matrix and the rows of the second matrix. So if I think about the 4, or actually I'll just write it and then explain it, it's way easier. So column 1 of A, I'll put that in parentheses so it's clear what I'm talking about. Column 1 of A. How many columns should I anticipate? N. So do call N of A times row 1 of B. How many rows am I anticipating? By design, right? Because I need the same number. Row N. This perspective is going to let me say that I could do the product simply as the column 1 of A multiplied by the row 1 of B, so on and so forth with a sum. Column N of A times row N of B. And if you like to be slick with your discrete math knowledge that you definitely apply every day, a summation I is equal to 1 to N of col IA times row IB. Now you might be thinking, well, why are we calling this suddenly col 1A? It's a more formal way to express what we've been thinking of as our A1 through AN, but now in this context, okay? Okay, questions about what the notation means. So does this expansion, can you read this expansion? Could you plug and check? Okay. And in that case, what I'm going to do is I'm going to use a few minutes here at the end to talk to you about proof writing. There's going to be proofs on these exams throughout the course. Why? Because it's an algebra class. That being said, I also believe in fairness. So I'm not going to ask you to do proof writing and proofs if I don't even teach you what basic syntax, the basic proof language, and the basic structure of a proof. Fair enough?
Yeah.
So if I show you those words, the language to use, the process, in general, practice it, okay? And you might be thinking, how do I practice proofs if my Pearson doesn't give me anything to practice proving? Well, as you're reviewing for exam 1, and you're looking at some of those theorems, some of those theorems are actually pretty straightforward in the sense that they're not really too difficult to prove so long as you have memorized your definitions. So get used to that rhythm of, you don't have to prove every single theorem, but as you read along in a math textbook, read actively. Mentally try to at least map out, like for you programmers, the pseudocode. You're not actually doing all of the fine details, but you can kind of pseudocode a problem in your head for an algorithm of how you would actually get from point A to point B. So it's a similar kind of process. That mental exercise is really, really going to be helpful. Okay, moving forward. So, elements of proof. Best part is you think of this as just a recipe. So you will be given, so the actual thing that you're being asked to prove, so some statement or some theorem, this is what you're being asked to prove. And so you say, okay, prove. The first thing you're going to want to do is articulate what the action, what the statement is. So articulate the task. Most people hate proofs because they sit down to a proof and they never actually just articulate the question. What are you even trying to show? Obviously, it's not that fun to prove something if you can't even name the thing that you're trying to show. So name it, That should be how you start every single proof. Name what you are trying to show. And second, frame the task in light of given definitions. When you're given a statement, 10 times out of 10, you will be able to take the vocabulary that is presented to you in that task and then now reframe the task in light of what that vocabulary even implies about the nature of the task. Again, proofwriting is not very fun if you don't know your definition. Because if you don't know the definition, you don't know the rule that you're supposed to be following. It's like playing a game. It's like playing Mao for the first time. And your friends are bullying you because you don't know any of the rules of Mao. And that's kind of the point of the game. But proofs don't do that, okay? You can know the rules to the game. And the rules are called the definitions. Okay? Sometimes it's a theorem. So I'll actually add it here. Sometimes it's also your theorems that are known and propositions, corollaries, things like that are given to you, okay? But most of it's definitional. So say you're asked to prove that something is linearly independent. Well, gee, don't just start shooting. Frame the task in what linear independent is, okay? If you can articulate what it means to be linearly independent, your task is suddenly 10 times easier than just being like, I don't know, look at it, okay? So, although that's what topology is like. Or say you were like, I have a set of vectors, and then here's some other vector. Can I show that this must be in the span of that set of vectors? Okay. What's the span of those vectors? Articulate the problem in terms of your definitions. It will make it so much easier, okay? And the next theme, use all the given, I call them ingredients. No proof statement, no task that you're given is going to give you redundant information. So have you ever finished a Lego set and then you had like those 7 random pieces that you didn't use that you know should not be extras? That's a terrible feeling because you know you did something wrong then, right? The build is not what it's supposed to look like completely. It's not built correctly because you didn't use all of the pieces. So in the problem statement, extract out all of those pieces. If you're not incorporating all of the details definitionally or logically that have been provided, you've missed the point somewhere. You've missed some sort of insight, you've missed some sort of logical connection, and you've probably made some sort of fallacious claim at some point, okay? So use everything. Your proof statement will never tell you more than you need to know, and it will always be just barely sufficient, the minimum amount of information that you need, okay? Some helpful language. Let. To declare for the computer scientist, declare your variables. Okay? The objects that you're going to interact with, don't just make them up as you go. Tell the person who's reading your proof what you're interacting with before you go into it. Okay? This is huge. I want to see this. Let. So if you have a set of vectors and you want to designate it, say you have a matrix, you need to show that maybe 2 matrices, their product is equal to the identity. Okay? Well then, don't just spawn them out of it into nowhere. Tell me that they exist. Let A and B be n by n matrices, okay? Some other things. We see that. Make observations about the problem. This is a really, really useful formula to use, especially when you're in the articulate the task stage. We see that this definition says blah, 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 blah. And if that definition is that way, then you can actually start moving from there logically. On the flip side, there's another really useful one. The other WST is we show that. This is now where you've gone from defining what's in the problem, observing what the definitions and the terminology actually do to impact the type of problem you're doing, and now you're going to do something. You're going to make a conclusion. You're going to draw a logically necessary conclusion entirely derived from the ingredients you started with and the observations you've made about the definitions and existing theorems. To we show that statements. Okay? Does this help? The goal over the course of the year, I want to have little sessions like this. Demystify the proof writing process. Because it's not that difficult. It's just, it's taught really poorly. Actually, the way it's taught is you go to grad school, you get your first real analysis textbook, and the professor says, you can't do that? I don't care. And then they'll fail you, and then you retake the class over and over and over again until you figure it out. Okay? I don't like that, so I'm showing you. Make sense? So you will need to use this on exams moving forward in the class. Any questions?
So, I don't know if we have time for it, but is there like a super simple example? I mean, like super simple proof that you could kind of like show like the
1 equals
Let's
1.
prove
the
that.
pseudo.
Actually, yeah, I can show you something real fast. Well, no, it's 2 away.
1 equals.
Do you guys need to go?
No.
Yeah.
Okay.
No.
If you want, I will record. No, I can't. I'm not going to overcommit myself because I'm already 7:30 to 7:30. We'll hit it in the exam review. I'll do a basic exam. All right, you guys have a good day.
We'll hit it in the exam.